Have you ever stopped to think about what's really going on inside your phone, your laptop, or, well, pretty much any piece of tech you own? It all feels like magic, right? Well, today we're going to pull back the curtain. Because it turns out our entire digital world is built on just three fundamental ideas. Three simple magic tricks that, once you understand them, explain everything. I mean, think about it for a second. What could a massive supercomputer, a machine busy solving the most complex problems imaginable, possibly have in common with the headphones you use to listen to music? One is unbelievably complex, the other seems so simple. But the truth is, if you could zoom all the way in, you'd find they're built from the exact same stuff.
And that's the big secret. All of this incredible technology, all this complexity, it all boils down to just three core electronic concepts. It's kind of wild when you think about it. And today, we're going to walk through all three so you can see exactly how the magic works.
Okay, let's dive right in with trick number one. And honestly, this is the big one. We're talking about the absolute bedrock of all modern electronics, the transistor. This little thing is maybe the most important invention of the last century. No exaggeration.
So what is a transistor? Well, at its heart, it's a tiny little device that's really good at two things: switching and amplifying. You can think of it as the fundamental atom of our digital universe. Your computer chip has billions of them packed inside. And you know, the best way to wrap your head around this is to picture a water faucet. A tiny, effortless twist on the handle can control a huge, powerful flow of water, right? That's exactly what a transistor does with electricity. A tiny little input signal controls a much bigger flow of current. That simple idea, a little effort getting a huge result, is the key to, well, everything. Now, we're not going to get lost in the weeds here, but it's good to know that these little switches come in two main flavors. You can kind of think of them as a push button versus a pull button. They both achieve the same thing, opening a gate. They just do it in opposite ways. And having both gives engineers a ton of flexibility for designing circuits.
And those flavors break down into two main families. One type, the BJT, is like a faucet that needs a little trickle of water flowing through the handle just to keep the main flow going. The other type, the FET, is more like a touch-sensitive button. You just apply a little bit of pressure or voltage and the main flow starts. No trickle needed for the control itself. And that one is the secret sauce that makes the chips in our computers so incredibly fast.
So this brings us to the transistor's first big trick. It's a nearly perfect, unbelievably fast switch. A tiny electrical pulse can flip a circuit from off to on. Simple enough, right? But now imagine doing that millions or even billions of times every single second. That's it. That's the foundation of all computing. A whole universe built on just two states, on and off, ones and zeros.
But wait, there's more. A transistor isn't just an on-off switch. It has a second, equally amazing trick up its sleeve: amplification. This is how we take a tiny, barely there whisper of a signal and turn it into a powerful roar.
So if fully off and fully on are the two extremes, the real magic happens in the space right in between them. It's called the active region. And in this zone, the transistor stops acting like a simple light switch and starts behaving like a super precise dimmer switch. It's not just on or off anymore. It's a controllable valve that you can set to 10% open or 47% open or anywhere you want.
And here's how it works. First, you set up the transistor so it's idling right there in that active region. Then you feed it a tiny little signal, say from a microphone picking up your voice. The transistor uses the tiny wiggles in that signal to control a huge flow of current from a power supply, perfectly mimicking the input signal, but way bigger. The whisper becomes a roar. That's amplification.
Now, as you can imagine, building a really good amplifier from a bunch of individual transistors can get pretty tricky. So engineers came up with this brilliant little shortcut to make life easier: the operational amplifier, or as everyone calls it, the op-amp.
An op-amp is pretty much what it sounds like. It's an amplifier in a box. It's a whole integrated circuit that takes all that complex transistor stuff we just talked about and neatly packages it into one simple, reliable, and incredibly powerful little component. It's like someone did all the hard work for you.
Okay, so here's the genius part. By itself, an op-amp has an almost infinite amount of amplification power, or gain. It's like a microphone turned up so high all it does is screech. But the trick is, we use really simple external parts, like a couple of resistors, to feed a little bit of the output back to the input. And by doing that, we can tell the op-amp exactly how much to amplify. It lets us tame all that raw power and makes it predictable and incredibly useful.
All right, so we can switch, and we can amplify. That brings us to our third and final magic trick:
How does a circuit create a signal out of thin air? How do you give it a pulse, a steady rhythm? The answer is a beautiful concept called oscillation.
Oscillation is basically when a circuit learns to generate its own continuous, repeating signal, a kind of electronic heartbeat. And the craziest part is, it does this all by itself, without any kind of signal coming in from the outside. It uses a clever trick called positive feedback.
You know the best way to picture this? Think of a swing on a playground. To keep it going higher and higher, you need to give it a little push at exactly the right moment in its arc. That perfectly timed push, that's positive feedback. An oscillator circuit does the same thing. It takes a little piece of its own output and feeds it back to the input at just the right time to keep itself going.
And the way this process starts is just amazing. It literally begins with nothing. Just a tiny, random flicker of electronic noise that exists in any circuit. The amplifier grabs that tiny spark and makes it bigger. The positive feedback loop sends it back around to be amplified again and again, making it grow. Meanwhile, a filter makes sure only one specific frequency gets to loop around until, very quickly, you have a strong, stable, predictable electronic heartbeat.
And what's so cool is the amount of control we have. By choosing a very specific recipe of simple components, a few resistors and capacitors, we can tell the circuit exactly what note to sing or what frequency to oscillate at. This is how we create the perfect, stable timing signals that all our electronics rely on.
Okay, let's take a step back. We've got switching, we've got amplifying, and we've got oscillating. 3 core tricks. So let's bring it all home and talk about why these simple ideas are just so incredibly important.
Because these 3 things, they literally build our entire world. Switching, those billions of transistors flipping on and off, that's the raw logic inside your phone's processor. Amplification, that's what takes the faint signal from a Wi-Fi antenna and makes it strong enough for your laptop to use. And oscillation, that's the clock, the steady, rhythmic metronome that synchronizes every single operation inside almost every digital device you own.
It's a really amazing progression when you think about it. We started with just a simple on-off switch. Then we figured out how to turn that switch into a controllable valve to make tiny signals huge. And finally, we taught that valve how to feed itself, to create its own steady, rhythmic pulse out of nothing.
So these 3 fundamental ideas, they aren't just some old principles from a textbook. They are the active, living foundation of all the technology we use every single day. They gave us the modern world as we know it, which really only leaves one question. What incredible things are we going to build with them next?